So today we're going to continue our work with probability lesson 10.2, and we're going to expand it to experimental and theoretical probability. Theoretical probability is the probability we've already been doing, but we're just going to give it a fancier, more mathematical name. So to start, when you conduct an experiment, as we did with flipping a coin and playing a rock, paper, scissors game, the relative frequency of that event is the fraction or percent of time that the event occurs. And it's written in much the same way we've been writing our theoretical probabilities. If I asked you what is the probability of flipping heads on a coin, you would have told me 1/2, because it's one time out of the total possible number of outcomes. It's kind of the same idea. I would say the number of times a coin landed on heads over the total number of times I conducted the experiment. And with that, then the experimental probability is the very same thing. So relative frequency and experimental probability are two ways to say the same thing in math. So it's the number of times the event occurs over the total number of trials. And experimental probabilities do eventually become theoretical or match the theoretical probabilities that we've said in class, and I showed you this with your work from flipping a coin and rock, paper, scissors. But that it takes so much time to conduct these experiments to get them close to the theoretical probability that we don't conduct the experiments every time. We trust the theoretical probability, but we're okay if the experimental probability comes out somewhere near the theoretical one. So on here, the bar graph shows the results of rolling a number cube 50 times. What's the experimental probability of rolling an odd number? Well, you would have told me it was 1/2 if it was theoretical. But here, you count up the number of times it landed on an odd number, 1, 3, 5, so you do 10 plus 8 plus 11, and you get 29. So the probability of odd, you write it just the way you did your normal probabilities, is 29 over 50. And you can turn that into a percentage by doing 29 divided by 50 times 100, and you get 58%. So you can see that it's not quite the same as our theoretical probability. It's pretty close. If we did more experiments, it certainly would start getting closer and closer to that 50% mark. So then you guys did the same thing, but for an even number, you could have added up the even outcomes, or you could have just done 50 minus 29, because everything that's left are the even numbers from the last slide, and you get 21 over 50. Sometimes they're going to ask you to use an experimental probability to make a prediction about the future, or create a pattern or a trend. So they said it rained 2 out of the last 12 days in March. If this trend continues, how many rainy days would you expect in April? I expect that some of you would have found this problem difficult only because you didn't know how many days there were in April. There are 30, and they're going to give you numbers that are compatible. There's no way to make 2/12 work with 31, or even 1/6. But I can make its reduced form, 2/12, or 2 rain days out of a total of 12 days, or 1 rain day out of 6 days, match up with 30 days. So 6 can become 30 by multiplying by 5. So 1 rainy day multiplied by 5 is 5 total rainy days in April can be expected. And so we did the same thing with the clothing company. An inspector finds 5 defective pairs of jeans in a shipment of 200. So if the trend continues, how many would you expect in a shipment of 5,000? So we discovered that 200, in a shipment of 200, that would occur 25 times. And if that happened 25 times, you'd have 5,000 pairs of jeans. So we just multiplied by 25, and we got 125 pairs of defective jeans in a shipment of 5,000. And the theoretical probability, it's the same definition as probability from our lesson on just probability last week, 10.2. So now we're just giving it its fancier name, because in theory, these are the probabilities. We know that in the real world, there's so many factors that can affect the outcome of an experiment, whether it's the person or the material or the machine. Things just don't always happen in that perfect vacuum. But so now our perfect vacuum probabilities are our theoretical, or in theory, probabilities. And so they're going to ask you to just do a little bit more practice with that theoretical probability. So you randomly choose one of the letters shown. The probability of choosing a vowel here is 3 out of 7. Probability of a vowel, 3 out of 7. So then what is the theoretical probability of choosing an X? Well, there's one X out of 7 blocks, so 1 out of 7. They can ask you to use the probability to kind of undo that simplification like we did with 10.2. So the theoretical probability of winning a bobblehead is 1 out of 6. So 1 bobblehead section out of 6 sections total, or 1 win out of 6 possible outcomes. So the wheel has 3 bobblehead sections. So if I can get 1 bobblehead out of 6 possible outcomes, then to get that 1 to turn into a 3, I have to multiply by 3. So that means 6 times 3 is 18. So there are 18 sections in the wheel. And I basically took 1/6 and brought it back to its unsimplified form, 3/18. Sometimes they're just going to ask you to use the probability to figure out an expected outcome. So in this case, the wheel was spun 540 times. If the probability remains 1 out of 6, then you end up multiplying these two numbers. It doesn't make sense to add, subtract, divide to figure out the answer. So if every 1 out of 6 times someone wins a bobblehead, then you multiply that to 540 and you get 90 bobbleheads. This one was fun because the probability wasn't given to you as a fraction or a ratio, it was given to you as a decimal, and being able to say this decimal correctly, 6/10, and then not simplifying it to 3/5 right away actually makes this question very simple. Because if the theoretical probability of spinning an odd number on a spinner is 6/10, that means there are 6 odd numbers for every 10 sections. If the spinner has 10 sections, then the number of sections that have odd numbers is 6. So the answer's already built into the problem. It's just seeing if you can understand. And this is where they kind of roll it all together, comparing them. So they'll ask you to find the experimental probability, in this case, odd, for rolling a number cube 300 times instead of 50. Remember, it was 50, the bars were all different sizes. Now that the experiment has been continued, you can see that the numbers are starting to get closer together. So 147 over 300 reduces to 49 over 100, or 49%. If we said in theory, we would say it's 50%. And then how does it compare with the theoretical probability? We would say that they're close. They're almost the same. If we're within a few percentage points, we're going to say that they're the same, they match. And I kind of compared this to the first example already, that as the experiment was continued and more results are added in, the theoretical probability, the experimental probability rather, started matching the theoretical probability. And if you did this comparison, you would see that these are also within 1% of each other. They're very close. So that's our lesson on experimental and theoretical probability.